Welcome back to the channel. My name is Daniel with CMC Learning, and today we're going to be having a look at series. More specifically, in the sort of A-level Year 13 topic, we bring up this idea of sequences and series. I think first it's good to cover the difference between them. A sequence of numbers simply refers to a list of these numbers, depending on either arithmetic or geometric, how these sort of terms come along. Whereas a series is referring to a sum of these terms. We're going to have a look at a few equations and sort of where they come from, and definitely how important they can be. So I say we jump right in. We're going to get started with the arithmetic sequence. So an arithmetic sequence is just a list of numbers where there is a common difference between them. We can write the nth term of this sequence as follows. So for example, the first term of the sequence is going to be given by A, and that is how we define A. A is the first term of the sequence. D is this common difference between each term. So we can see that as n increases, we're adding more of these differences on and on. So in our sequence, we're going to have a list of these numbers, but I'm more interested in sort of the sum of all of these numbers. So let's have a look at how that comes along. Let's start by listing off, for some general arithmetic sequence, all of the numbers in our series, so all of the numbers in our sum. We're going to index these by values of n. So when n is equal to 1, our term is just a, isn't it? When n is equal to 2, our term is a plus n, which is 2, minus 1, which is just 1, multiplied by d. So we're left with this term here. When n is equal to 3, we have a plus, in this case, will be 2 multiplied by d. We might just write that as 2d. 2d. And then we're just going to do this sort of dot dot dot, these ellipses, just so we can continue on the series. And we're going to go to values up to n. So we're doing this for a general number of terms in our series. So what we're going to do here is we're going to look at the last 3 terms. So obviously our last term is going to be n. The term before that is going to be n minus 1. And the term before that we're going to call n minus 2. So maybe you would have seen this method written, but it's good to sort of explain what each of these terms are. Essentially, the way we can write down this term in our series, just have a look at this equation up top. So if we just sub in n minus 2 in that expression, I also forgot to put a plus here, what we end up with is a plus n minus 3 multiplied by d. It's really important that we understand where that comes from. We then look at the second to last term. We have a plus n minus 2 multiplied by d. And of course the last term in this series, we say n is equal to n, so it's the last term. For example, if n is equal to 100, this would be the 100th term. So essentially sub in 100 as n. But we just write this as the nth term, which in this case is a plus n minus 1 multiplied by d. Let me tidy up this expression a little bit. What we can see here is essentially we have to find a way to simplify this series. It's a bit all over the place. So there's a common trick. We can say that all of the above is equal to. We can say all of the above is equal to Sn. So just the sum up to n terms. Now what we're going to have to do, in order to see if there's a trick here, let's write S of n, but let's reverse the order. So say I have some terms, 5, 7, and 9, for example, these odd terms. I can do 5 plus 7 plus 9. I can also do 9 plus 7 plus 5. The order does not matter when we're doing addition here. So essentially we're just going to replicate what we have above and just completely reverse the order. So we have n is equal to n. So this is n minus 1 multiplied by d. When n is equal to n minus 1, we have n minus 2 multiplied by d. And of course all these terms are added to each other. N is equal to n minus 2 with a plus n minus 3 multiplied by d. Then we'll do the very same thing. So we're doing 3 n's at the very beginning and very end of our sequence. So we can do our dot dot dot. Of course these terms are added. Then we have our n is equal to 3 term, which is a plus 2d. Our n is equal to 2 term, which is a plus d. And our n is equal to 1 term, which is just a. It is sometimes good to put these terms over here in brackets so we can understand what's happening. And the trick that mathematicians exploit to figure out this sum, essentially they look at 2 of these sums added together individually. And what I mean by that is, let's have a look at the first term in our normal order, if you will, which is going from the smallest to the largest value of n. We have this value a here. What we're going to do is we're going to add that to the last term in our sum. This does sort of make a little bit more sense when you consider 2 separate sums. If I'm adding the first term and the last term of these 2 identical sums s of n, I'm going to be left with 2 of s of n. Essentially I'm adding one series of numbers to another series of numbers, and inside those series I'm obviously adding these numbers. So what I'm left with is 2s of n. I can say that that is what happens when I add both of these series together, but we're just going to consider individual terms for now. So the sort of quote-unquote first term here, we're going to be doing a plus n minus 1 multiplied by d. Well, that's quite simple. We only need to add the a terms. So here we have 2a plus n minus 1d. Now what we're going to do, we're going to go through every single term. In this case, we know there are n terms, so we're going to go through the n terms of this, and I'm going to see if a pattern arises. So right now we need to do in a way, the second term, a plus d plus a plus n minus 2 multiplied by d. We can add the 2 a's. That just simply gives us 2a. So that's quite simple. But let's see if a pattern emerges. If I'm doing n minus 2 multiplied by d, we can write this out explicitly. We want to add this to the d term above. In this case, there's just 1d. If we expand this out, we get nd minus 2d. And on top of that, we're adding the value of d. So what we're left with is nd minus d. So 2d plus 1d just gives us d. And here we can factor out a d. We get n minus 1. Typically, people put the d on this side. But we can see that is completely identical to the first term we have, at least this last bit as well. So we're left with n minus 1 multiplied by d. And this is something that happens for each term. Here we've written out 3. We've only done sort of 2 of them, as I'm sure you can figure out on your own. If you add this term here and this term here, you should end up with exactly the same thing. So 2a plus n minus 1d. And the idea is this goes on for quite a few terms. If we have a think of how many terms this goes on for, it's going to be n times. So we're adding these pairs for different values of n. And this happens n times. So since multiplication is simply just adding a certain number of terms a certain amount of times, we can say that 2Sn is equal to n times what we have here on the right hand side. So, n times. So n times of 2a plus n minus 1d. If we have a look at this, well, in order to find the sum to n terms, which is what we defined above, the sum over all n terms, we just have to divide, in this case, by 2. And that gives us n divided by 2 multiplied by 2a plus n minus 1 multiplied by d, all in brackets. And this is the familiar equation that you've probably seen in your textbooks. Essentially just for n terms, you sub in n, you find your first term and your common difference, you can find out the sum to all those terms. So that is sort of a fairly simple approach. It is a bit contrived to say sum both of these series, on top of each other in a way. But by dividing by 2 at the very end, we maintain what we were looking for in the first place. So that is definitely, I would say, the easier of the two. We're now going to move on to geometric series. And this one is definitely a bit more contrived. So let's have a look. We can write the nth term of a geometric sequence as a multiplied by r to the power of n minus 1. In this case, a is our first term. R, instead of being a common difference, is more of a sort of term that we multiply between one term and another. So essentially, I can have 2, 4, and 8 as the first three terms of my sequence. In that case, the common difference would be 2. So I'm multiplying the previous number by 2. Okay, so the question has to be asked in this case, how can I find the sum to n terms? Well, we're going to do the exact same thing as before. We're going to manipulate essentially the sum and see if there's something we can do, and maybe add two of them together and see where it takes us. First, let's have a quick look at what is happening with sort of the first three terms and last three terms. We know the first term is a multiplied by r, a multiplied by r squared. Those are our first three terms. And our last three terms, a bit trickier to see, but we just simply set n is equal to minus 2 minus 1, or n minus 2, n minus 1, and n. In doing so, we see a r n minus 3 plus a r n to the power minus 2, or n minus 2. And the final term in this series, n minus 1, as expected. So the step for this is quite contrived, but let's have a look. Maybe there is a way we can include the sum to n terms inside of the sum to n terms if we multiply it by a certain factor. So what we should consider is the sum to n terms. In this case, every single term is multiplied by r. Let's see what that gives us. Well, the first term multiplied by r, ar. Second term, ar squared. Third term, ar cubed. In this case, we can see we're just increasing the index of this r term by 1. So we can keep going. For the last three terms, arn minus 2, arn minus 1. And the last term now becomes ar, the power of just n. So n minus 1 multiplied by another r just gets rid of that minus 1 index. So very good. What we have a look at, what we should have a look at here, is if there are any terms that match. And because essentially what we've done is just shifted our sum, we can see that we have some common terms. If anything, this term is sort of included in this ellipsis, and very similar with this term, it's sort of included just before this term here. So we can see that these two terms share almost every term. Keep these highlighted. They share almost every term except for two terms. This first term, a, in our sum to n. In this last term, a multiplied by r to the power of n. In this sum to n multiplied by r. So it's slightly different. And sort of analogous to simultaneous equations and that sort of working in GCSE, if we can find the difference between both of these sums, well, we can just cancel out these terms here. That's something, a bit more, it makes something more trivial. Essentially less terms to work with. And there are a few different ways to do this. We'll have a look at both. Let's try and do the difference between our sum to n and our sum to n multiplied by r. So we write something like this. And let's see what we get. Well, we can write out our entire sum to n. That's going to give us all of these terms up here. But then I'm taking away all of these terms here. We can see that these identical terms highlighted in green are just going to cancel out. So we're going to be left with an a from our sum to n, but then we're taking away an a multiplied by r to the power of n. A multiplied by r to the power of n. So these are the terms we're left with, and now we've completely, in a way, eradicated the sum. We're just left with two terms here, and we have a few sums to n, and as with the previous example, we want to make s of n the subject of our expression. So let's factor out s of n. We're left with 1 minus r. And on the right hand side we can also factor out a, can't we? This first term in our sequence. And what we're left with, we can see, we just simply divide through. We get a multiplied by 1 minus r to the power of n, all divided by 1 minus r. And this is a familiar equation that you've seen before, which is good. There is, however, another way to do this, as I mentioned. Here we're doing the sum of n minus the sum of n multiplied by r. Well, why don't we do it the other way around? Sum of n multiplied by r minus the sum of n. Let's have a look at what we get. So if we're doing this bottom sum minus the top sum, well, we can see that our sort of intermediate terms, highlighted in green, are still going to cancel out. But in this case, we're just going to be doing this term on the end here, minus this term up here. So here we're left with ar to the power of n minus a. And we can do the very same process as before. So let's factor out s of n. Yeah, r minus 1. And again, we can factor out a. R to the power of n minus 1. If we rearrange here, let's have a look. We end up with a multiplied by r to the power of n minus 1, all divided by r minus 1. So these are two forms of the very same expression. And even though some textbooks might mention to work with one over the other depending on your value of r, it's perfectly sort of formidable to use either. Both of them will definitely give you the correct answer. So if we have a quick recap of what we looked at the arithmetic series, quite a simple one, essentially just adding two copies of the sum together. Geometric is a little bit more different. In this case, we're doing the difference, all because we've multiplied one of them by r. We can find essentially those identical terms by doing so. And here we're left with two somewhat identical expressions that will both give you the sum to n terms. So I hope that helped. It's a good look at the three equations that somewhat show up. I've definitely seen some of these as maybe a free marker on the exam, so it's definitely very good to know how to cover these. If you'd like to see anything else from the textbook, do let us know in the comments below, and I'll see you guys in the next video. Thanks for watching.